Hi everyone, it's been a while, so let's get started. So this is the third part in our problem-solving methodology, which is going to be covering the physics example, and the one that I chose was Atwood's machine, a characteristic example that high school pupils are called to solve. So Atwood's machine consists of a pulley and two masses, M1 and M2, that one of them is greater than the other. So for this example, let's assume that M2 is greater than M1. So before we begin, we need to make two basic assumptions. Number one, the pulley is light and small. So this assumption allows us to consider the pulley as a peg. So it means that the pulley does not turn, and so the turning effects from the pulley are neglected. The second assumption is that the rope is not extendable. So this means that rope tensions are equal. So we will see this effect when we start the calculations. So in many physics examples, we come across the diagram of the problem. It is usually not required for the pupil or the student to produce the diagram based on the wording of the exercise. So most of the time, the diagram of the problem will be given. In this case, the Atwood's machine is a given, and what we are required to calculate is the acceleration of the two masses, so that we can calculate one of these two masses, given that one is known and the other one is unknown. So basically what we are doing is allow the Atwood's machine to move. We can measure the acceleration of the two masses by means of a timer and a straight edge and a ruler. And by using the relationship that we are going to derive, we can calculate the unknown mass. So before we start any relationship derivation, we must place all the forces on this diagram. Okay, so this is another piece of advice that I give to pupils and students. When you are given in your examination a diagram, you place all the forces on that diagram. You do not need to produce your own diagram on your piece of paper. Okay, so let's go right ahead. So first of all, we need to place the weights of the two masses. So M2G in this case, and the other one is M1G. Let's not use the W symbol for the weight because we are going to be confused with the work symbol. So let's not use that. Now, apart from the weights, each mass has also a rope tension. And as we have said before, based on the assumptions that we made, those two tensions are equal. Since we assumed that M2 is greater than M1, logic and intuition dictates that when left on its own, M2 will be lowered, so its acceleration will be downward, and M1's acceleration will be upward. Another consequence of the assumption 2 that we made earlier is that both of these accelerations of the two masses are equal. not only the rope tensions, but also the accelerations. So we have placed all the vectors of the problem on the diagram. Again, we do not care about the vectors or the forces from the pulley because it's very light and all the turning effects are neglected. Also, we need to take a direction reference for our vectors. So we choose that upwards will be the positive direction for all vectors. Not only the forces, but also the accelerations. You can take the reference downwards if you like. As long as we are consistent with our own direction reference, everything will be okay. So let's continue. So since we have forces and accelerations, we are going to be using Newton's second law. So as we have said in previous videos, we need to set our target. Our target in this case is the acceleration of the two masses, which we want to calculate based on the relationship between the masses of the two bodies. So let's go ahead and use Newton's second law, because this is the law that connects forces with accelerations. So for body 1, the resultant force acting on M1 is going to be equal only with the tension, which is positive since it's pointing upward, minus its weight. And since there are no other forces on the y-axis, we are setting this equal to M1, the mass of the object, times its acceleration. So this is equation number 1. So let's form another equation for the second mass. So the resultant force, sigma F, is equal again to T, tension is again positive, minus M2G, no other forces, so this is equal to minus M2A, because its acceleration is pointing downward. And this is equation number 2. Another tip at this stage, not only in physics exercises but also in mathematics exercises, is that when we have equations that work simultaneously, or a system of equations, is that we should label our equations so that we can keep track of them. In this case, we only have 2 equations, and because we do not care about calculating the tension of the rope, only the acceleration, because as we have said before, the target of our relationship is the acceleration, we need to eliminate the tension from these 2 equations. Because the 2 equations have exactly the same form, only a sign is different, the best course of action is to use the opposite coefficient method to eliminate the tension. So let's go ahead and do that. So let's rewrite our equations. So T minus M1G equals M1A, and T minus M2G equals minus M2A. So let's change the signs of the second equation. So this is multiplied by 1 and this is multiplied by minus 1. So we multiply every term on both sides of the equal sign with minus 1. So the first one remains the same, T minus M1G equals M1A, and the other one will become minus T plus M2G equals M2A. And then we add both of them up. So this is exactly the reason why the methodology is called opposite coefficient method, because now by adding these two equations together, the tension is eliminated. And we are left with M2G minus M1G equals M1A plus M2A. So we're getting closer now. We can take G and A as common factors from their respective sides. So M2 minus M1 times G is equal with M2 plus M1 times A. And now, since the target is the acceleration, we need to leave it alone on its side. So in this case, A will be equal with M2 minus M1 divided by M2 plus M1, and all of this is multiplied by G. And this is the relationship between the acceleration of the masses themselves, and G. Now, this exercise, as you can see, is theoretical. There are no given data. So most of the time, exercises are going to be giving you specific symbols, like in this case M2 and M1, and A, plane A, as the acceleration of the two bodies. So you're going to be using the specific symbols of the exercise so that basically you can produce a formula. Now, if the exercise is giving you numerical data, for example, M1 is 5 kilograms, the acceleration is 5 meters per second squared, and it's asking you to find the second mass, then we take it one step further. We rearrange the formulae or the relationships that we have produced, and by substitution we can calculate the quantity required. So this is another tip that I give to my students, is always produce the relationship without ever substituting the numerical data, and at the very end, if there are any numerical data, you just take it one step further. This is to practice not only solving theoretical exercises with just symbols, no numerical data, and also to be able to produce formulae without getting panicked that you are not given any pieces of data. So in this case, because we need to calculate the second mass with our given data, we need to solve our relationship that we have just produced for M2. It means that our target now becomes M2. So let's go ahead and do that. So first of all, let's take this form of the equation. M2 minus M1 times G is equal to M2 plus M1 times A. Let's use the distributive property of mathematics to distribute the common factors with the terms inside the brackets. So we are left with M2G minus M1G equals M2A plus M1A. And now we need to concentrate on the same side all the terms containing M2, our target. So in this case, we need to take M2G and leave it as it is, whereas M2A comes on the other side. So M2A, and then this is equal to M1A plus M1G. So now we are able to take M2 and M1 as common factors. So M2 times G minus A equals M1 times A plus G, and we divide with the coefficient of m2. So we are left with a relationship of m2 equals g plus a divided by g minus a times m1. So we solve our formula to the unknown or the target of the exercise. So once we solve for our target, only then we are able to make our substitution. So let's go ahead and do that. So m2 is equal to, we take g as 9.81 plus 5 meters per second squared, which is the given acceleration. Then we divide by 9.81 minus 5 in this case, and m1 is 5 kilograms. Now, some teachers require their pupils to substitute not only the numerical data, but also their measurement units. So in this case, 9.81 meters per second squared minus 5 meters per second squared divided by 9.8 meters per second squared minus 5 meters per second squared times 5 kilograms. Okay, I'm not too strict about this. This is only for pupils' practice so that they can confirm that only quantities with the same units can be added. So let's do the calculations. M2 now is equal to 1481 divided by 481. This is a dimensionless fraction because, as you remember, here we're dividing meters per second squared divided by meters per second squared. So all of the units are eliminated, and so we are left with a dimensionless fraction times 5 kilograms. And as we can see, the answer is expected to be in kilograms, just like the measurement units of mass. So by doing this calculation, we are left with 7,405 divided by 481 kilograms. So this is an exact answer because it is given as a single fraction. So if we want to see it as a decimal number, M2 is equal to 15.3950104 and so on kilograms. So this is a large number of decimal digits, but we only need the 3 most significant figures for the reason that G is given in 3 significant figures. So let's round this up. We start from the right and going to the left. So this is the first significant, the second, the third. We reached the 3 significant figures, and after that we see the next significant figure, which in this case is 9. So since 9 is greater than 5, it means that we can discard everything from this side forward and make that 0.3 into a 4. So our M2 in 3 significant figures is going to be 15.4 kilograms and 3 significant figures. And this is our answer. So this concludes my series on my problem-solving methodology. If you have any other questions, you can always comment below. Feedback and criticism is always constructive, and I would love to hear from you. Thank you and goodbye.